Okay, this next topic really goes along with what was in the last video. However, the last video was like at 15 minutes, so I decided to stop it. But what I want you to know, and I've already said this, is normally evaporation and condensation, if you're at equilibrium, occur at about the same rate. If you have like water sitting, just sitting out, the evaporation rate is greater than the condensation rate. And the reason for that is, in order for them to be the same, in an open container, you have to be in an environment that has 100% relative humidity, meaning that every time you put water into the air, water comes out. But normally the air can hold water, so as the evaporated particles leave, there's plenty of room for them to go and fly about through the air, and it just basically leaves your system and doesn't come back. That's why, in general, evaporation occurs faster. If you are at equilibrium, like a sealed container, eventually these two rates will happen at the same. They'll be the same rate, and therefore evaporation and condensation can be equal. Okay. So when you emerge from a shower in a dry room, you feel cold because evaporation is winning. And evaporation is a cooling process. If you if you do the opposite and go into a steaming sauna, right, you feel warm because the hot moisture is warming you, right? It's condensing on you instead of evaporating off of you. So how can evaporation and condensation take place at the same time? Well, it's not happening to the same. There's more than one particle of water. One particle of water over here is evaporating, another particle over here is condensing. So it's not the same particle that it's happening to. So they take place at the same time, but not on the same particle. Okay. All right, so that finished vaporization and condensation. But let's talk, or evaporation. Let's talk about the other type of vaporization, which is boiling. Uh, Basically, boiling has to do with when evaporation, when you have enough energy, you boil. But you actually boil at different temperatures based upon, so this is kind of a curve between liquid and gas. And this is pressure. Normally, water, if this is water, water boils at 100 degrees Celsius. But if you lower the pressure, like let's say we're in Denver, so here water would boil at a lower temperature in Denver because the air pressure is lower. And if I was to go into a vacuum, in a vacuum water can actually boil. In a complete vacuum, water can boil at just a little bit above freezing. So you can go down you can take cold water and make it boil in a vacuum. Because boiling, and this is what I want you to understand, you've been taught that, like, this definition of boiling. Boiling is when the temperature is high enough for half of the particles to have enough energy to vaporize. That's what you've been taught. But what you haven't been taught maybe is that boiling happens at different temperatures for different pressures. Because what boiling really is, make sure I have this over here. So I have this flask and I have liquid in here. There is air pressure. And that air pressure is pushing down. Okay? And then there's a certain propensity for the water to want to vaporize. So this is the vapor pressure. So this is vapor pressure. And that's the pressure of the vapor pushing upward. And then there's the pressure of the air pushing downward on this open container. When these two pressures are equal, you boil. That's the true definition of boiling. Boiling is not 100 degrees Celsius. That's the definition that we use a lot. But boiling is when vapor pressure equals air pressure. So the amount of heat you put into something will determine what the vapor pressure is. The more heat you put in, the higher the vapor pressure. And the air pressure basically stays the same. So if you take liquid water and you heat it up, until you've heated it enough to get the vapor pressure high enough, it won't boil. And when you've heated it to 100 degrees, it boils because now the vapor pressure and the air pressure are equal. However, if I take that same water and put it in a vacuum, I don't have to apply as much heat because it's already got enough energy because the air pressure above it is so much lower. So basically, boiling happens when vapor pressure equals air pressure. That's when boiling happens. Okay? And it's a type of vapor. Evaporation occurs when the particles that have enough energy escape. And that can happen below the boiling point. Now there are two different things to think. Like right here, 100 degrees Celsius at 1 atmosphere of pressure. This is what we call the normal boiling point of water. The normal boiling point is where does it normally occur, which means 1 atmosphere of pressure. At 1 atmosphere of pressure, the boiling point is 100 degrees. So that's the normal boiling point. Anywhere along this curve is a boiling point, just not the normal boiling point. Okay, so boiling. Boiling happens when vapor pressure equals air pressure. Okay? And there's one particular boiling point called the normal boiling point that happens at 1 atmospheric pressure or 760 millimeters of mercury or 101.3 kilopascals of pressure. So the change of phase from liquid to gas is boiling. Okay? And boiling happens everywhere. It happens throughout. Bubbles, and as soon as that temperature is reached, that's when you start to boil. Okay. If you increase the atmospheric pressure, it takes more, the molecules in the vapor must move faster, they must have more energy, so it takes a higher temperature to boil. At lower pressures, such as high altitudes, boiling point decreases. And if I put something in a pressure cooker, which increases pressure, the boiling point increases. So that's one way to cook things at a higher temperature at high altitudes is to use a pressure cooker. Now boiling, like I said, is a cooling process because the higher energy particles leave. So if you, so here's something about like when you're boiling, once the pot is boiling, to get it up to there, you have to put a lot of energy in, so you want high heat. But once something starts boiling, it only takes a little bit of heat to keep something boiling. You only need enough heat at that point to counteract the cooling caused by vaporization. So a lot of people think if you keep the heat up higher, that it will boil hotter. It will boil more vigorously, but it will not boil hotter. The temperature of boiling water will remain the same at a given pressure. The temperature doesn't change during boiling, so having more heat doesn't mean a hotter container. It may feel hotter because the more vigorous boiling makes there be more steam, and steam is hotter than the boiling water. Steam can be, you can get high pressure steam at 300 degrees Celsius, but usually, 110, 120 degrees Celsius coming off of the water, but it's going to warm that air around the steam a lot. And that's one reason why you can get a steam burn. It's actually, you'll get a burn faster from steam than you will if you just stuck your hand right into the hot water, because it'd be a lower temperature. You wouldn't want to leave your hand in boiling water though, or that would not be a fun day for you. So since boiling is a cooling process, would it be a good idea to cool your hot and sticky hands by dipping them into boiling water? Absolutely not. The water is being cooled. Remember, boiling cools the water, but it warms the environment, and your hand would be the environment. So you would be warmed, the water would be cooled. So keep that in mind. When we say that vaporization is a cooling process, you're talking about the thing being boiled. What's around it is warmed. Okay. So what is the effect of pressure on boiling temperature? Higher pressure, higher boiling temperature. Lower pressure, lower boiling temperature. All right. Oops, I meant to go this way. All right. So now we're going to talk about this freezing and melting. Freezing and melting in general. And there's a special thing about freezing and melting we're going to talk about, which has to do with freezing point depression, and it also has to do with boiling point elevation. In fact, maybe I'll talk about that now since they mentioned it here. Let me go to another sheet here. And this is actually a physical, not a chemical process. Okay, let's say that I have a solution in a beaker. Okay, so I have this beaker here, and it has a solution in it, and there are particles in here. For evaporation or boiling to occur, the particles have to leave. All right. For condensation to occur, right? Well, let's just do that first. For boiling to occur, particles have to leave. Now let's say that I put some other particles in here, like salt. If that salt concentration is high enough, it can actually physically get in the way of the particles. So instead of the particles hitting the surface of the water, they had enough energy to escape, but instead they hit like a sodium or a chloride ion. And they instead of leaving, even though this particle has enough energy, it bounces off that salt particle and goes back into the and stays in the liquid form. And maybe the salt particle gets a little bit of energy. So this is called boiling point elevation. Now, likewise, you have what we call freezing point depression. So let's say I have this same vial. So here I'm increasing temperature, and in this case I'm lowering the temperature. Okay, so I have the same water particles and the same salt particles in here. In order for freezing to occur, or to go from a liquid to a solid, you can call that deposition, fusion, whatever you want to call it, these particles of water have to be able to come together. And when they do, since they have low enough energy, they now turn into a solid. But some of these particles will try to make it, and this salt particle will physically be in the way. So it makes it harder for the object to freeze. And usually the more salt particles you have, the harder it is for something to freeze. And that's why you put salt on the roads in the winter, because it lowers the freezing point of the water so that ice forms at a lower temperature. Now, if it gets too cold, they put sand down, because the sand just sticks on the surface and gives you traction on top of the ice. You put salt down when you want to melt the ice. You put sand down when it's too cold to melt the ice, so you just need traction on top of the ice. But the point is, putting something else in a solution does both of these. It elevates boiling point and it depresses freezing. This is one reason why we add salt to boiling water before you cook. It does two things. It flavors what you're boiling, so it adds a little salt to it, but it also raises the boiling point so that you can cook it faster because you're boiling at a higher temperature by adding salt. And then we add salt to reduce freezing. So these are the two processes that it's talking about freezing. So we're still talking about freezing, going from water to ice or liquid to solid. But at the same time, they're going to talk about this physical process of elevating the boiling point and depressing the freezing point. So in general, dissolving something in a liquid lowers the freezing point and also tends to raise the boiling point. Now that change of phase from liquid to solid we call freezing. You'll also see this called, sometimes this will also be called deposition in some books, or fusion, which can be both directions. You'll see it called different things. So we've already talked about the properties of water in chemistry, but just so you know that pure ice has this, and there are, like, I've read over something like 60 or more different structures that water can take depending upon the pressure and how long it's under cold temperatures. That's why glaciers tend to turn blue. It's actually a different structure of ice. This is the type of ice that you're going to see in your freezer. This is why ice typically has a lower density than water, because it has this open area in here. So that's a special property of water that allows solid water to float. If I took a piece of solid iron and threw it into a vat of molten iron, the solid iron would sink to the bottom, unlike ice, which rises to the top of liquid water. So what effect does dissolving anything have on freezing point, though? And it depresses it. It makes it lower. Okay. Now I already said that already talked about boiling and freezing at the same time, but I'm going to come back to it. There's this triple point. It's called the triple point. There is a point where the pressure is so low and the temperature is low. So if I lower the pressure, things boil easier. But if I lower the temperature, they boil harder. And if I lower the temperature, they want to become a liquid or a solid. So if I take a gas, if I lower the temperature, it becomes a liquid. If I lower the temperature more, it becomes a solid. But if I lower the pressure, pressure has the reverse effect. Lower pressure, and all of a sudden, what used to be, as I lower the pressure here, notice how I can make a liquid into a gas by lowering the pressure, right? So if all I do is lower the pressure, if I'm at 100 degrees Celsius, or let me go up here. If I'm at, I didn't draw the best. Where'd my pen go? Let's say that I'm at, like let's say 5 atmospheres up here, and I'm at, this, I'm at like 0 degrees Celsius. So I'm a liquid, right? It's in liquid form, even though it's high pressure. It's a liquid form. If I lower the pressure, it'll eventually become a solid. If I lower the pressure enough, it can eventually become a gas. Even though it's at 0 degrees Celsius, you can have gaseous water at 0 degrees Celsius if the pressure is basically zero, a pure vacuum. If you go to 0.01 atmospheres, that's called the triple point. That is a point where, and we talked about this in chemistry, where you can be both a solid, a liquid, and a gas at the same time. And I've done this before. I've used, although I haven't used water, I'll probably link a video, and I'm going to put that, make a note to myself and say link triple point video, where you can actually see the different, see boiling and freezing in a liquid. So you take a liquid and you put it in a vacuum. You'll actually see some of the liquid boiling while simultaneously some of the liquid is freezing. And that's because you're at this triple point where all of the processes occur at the same time. And I've done this before with water, but it takes about 20 minutes for the vacuum pump to get low enough pressure constantly running before you finally, and that slowly cools the water inside of it until you eventually get this boiling and freezing water happening at the same time. Now the boiling cools the water and the freezing warms it back up, so it maintains the same temperature basically. So what can cause boiling and freezing to take place at the same time? If you have the right conditions of temperature and pressure. If the temperature and pressure are right, meaning, and it's almost always low pressure. So if you lower the pressure enough, you can get boiling and freezing to take place at the same time. Lower pressure being the key there. Okay. Now another process, which is a way of freezing, is regulation. And I'm just going to quickly get regulation. All I want you to know is what it means. Regulation happens when something expands so rapidly that it freezes. So if you increase volume, and let's think in terms of, remember, PV is equal to nRT, all right? If I expand something so rapidly, that and the pressure decreases rapidly, what usually ends up happening is pressure wins, and so this side over here goes down, and since you have the same number of particles and since R is constant, the temperature goes down. So, and this works really well with water. So things that contain water, you can freeze them really well. All right. So if I remove the pressure, so I take something and I quickly vacuum, and I put it under like a quick vacuum. So I have something that's like 20 degrees Celsius, room temperature, and I put it in a vacuum and I suck all the air out really quickly. So the pressure goes down very rapidly. The pressure decreases so rapidly, and it's a liquid, so the volume doesn't change that much. The volume will expand a little bit as it freezes, but since the pressure goes down so rapidly, the temperature goes down and you freeze it. So that's called regulation. If you decrease the pressure fast enough, you can freeze things. And actually increasing pressure can melt things. This is actually back in the days when you would have ice salesmen, you don't want to waste ice. So you don't want to cut it because cutting frays off and you have shards of ice going everywhere. So what you do is you would take a wire, a thin wire, and you would put weights, and these weights would apply pressure along where the string is. So the pressure, where the pressure is applied, so the exact opposite of regulation, the pressure increases the temperature right along the rope. And what happens is the rope just falls through the ice and basically cuts it in half. You pull it apart and you cut the ice in half without losing any of it, because all you do is turn a little bit of it into liquid, and as you pull it apart, if it's cold enough, it'll refreeze and you're not losing. And anything that you do lose, because the wire will be covered with a little bit of water, is much less than you lose from cutting. So you do have to separate as this is happening. If you don't do anything, the wire will just go through and it'll freeze behind it, and you just end up with the same block of ice that you started with. So why do so few substances undergo regulation? Well, the reason for this is, where do I want to, I thought I had, you really have to have this open structured crystal. So you have to have something like water where the density decreases, if ice has a lower density, if the solid is lower density than the liquid, this will work because the pressure you put on it is crushing it, so it's reducing the density, which turns it back into a liquid. So regulation occurs because of, if I go all the way back, because of this structure of water, this open, low density, solid structure. And I think that's a good place to stop, and then we'll do one more video.